Hey and welcome to this tutorial on how you can model the mechanical behavior of soft polymer foams. So these are foams that are really soft and squishy and not the brittle materials that sometimes are used as well. So if you have a material like that, what kind of material model would work? And why would you use such a material model versus something else? That's really what I want to talk about here today. The first question though is really, can we not just use a hyperelastic material model? Hyperelastic material models are very often used for rubbers, obviously. Can we use it for rubbery foams too? Let's take a look. So I've started to look at a hyperelastic material here. This is the most basic one that's available. That's the Hookian hyperelastic model. And the key question here really is, what happens if you have a material that is very soft but also has a small Poisson's ratio? So if the Poisson's ratio is much lower than 0.5, can you still use the Hookian hyperelastic model? So I plotted in this figure here the Poisson's ratio as a function of the applied strain. There are two material parameters in the Hookian material model. We have the shear modulus and the bulk modulus. And I fixed the shear modulus to be 1, and I looked at different bulk modulus values. If bulk modulus is 100, then of course the material is almost incompressible all the time. Not really good for a foam. Kappa equal to 10 is still too high. This is a very high Poisson's ratio and often is not suitable for soft foams. So then I started to go down. How about if kappa is equal to 1, which is equal to the shear modulus? Well, at small strain, you'll get a Poisson's ratio that is about 0.1 or 0.15. And that's pretty common for many of these soft foams. But the problem that you can see here is that the Poisson's ratio changes a lot with applied strain. You can't have a Poisson's ratio that's independent of the strain. You get this crazy behavior, particularly compression here. Not such a good model for soft foams, obviously. How about if we use a yaw hyperelastic model? The yaw hyperelastic model has the interesting ability to have higher order bulk modulus terms, as you can see at the bottom here. In this case, let's focus on the green line here. I set C10 to be 1. I set C20 to be 0, C30 to be 0. So these are not here. And I use a D1 value of 0.8. So that's even slightly lower than C10. From the previous slide, we know that that's not going to be so good because the Poisson's ratio will go negative in compression. So I added additional terms here, specifically D2. So if I added a little bit positive D2, 0.2 in this case, the energy in the material will increase as you compress it or pull it in tension, as the volume changes in essence. And that allows us to have a more reasonable Poisson's ratio as a function of the applied strain. But it's still not very constant. It changes a lot, and you can't really control the shape of this curve. So it's a problematic situation. So I wouldn't say that you should use this kind of hyperelastic model for foams. That's not the recommended way. The final traditional hyperelastic model one can try is an alternative representation where the stress is not given by the deviatoric part of the B tensor, if you remember. Instead, it's B minus 1. So this is not the traditional decomposition of the energy into deviatoric and volumetric parts. But by not doing that, you often get a little bit more realistic Poisson's ratio for materials. So some people use this for rubber-like materials. But as you can see here, it's not really super great for foams either. We don't control the Poisson's ratio good enough. So I think we need something better than this. And the answer to that is what I call the hyperfoam model. So a hyperfoam model is a specific type of hyperelastic material model that has some particular features to it that makes it better suited for soft foam materials. And the history about these hyperfoam models is a little confusing. I tried to go through and figure out, like, where does this come from? It turns out the different finite element programs call this type of model a little bit with different names. They have almost the same equations, but they have very different names. Abaqus call it Hyperfoam, and they refer to a paper by Storakers who was a professor at the Royal Institute in Stockholm, which is where I studied a long time ago. I think I met Storakers once actually in the past. But if you read his paper, he talks more about work by Professor Hill. So really, maybe it's not clear exactly what's going on there, but the Hill equation is the one at the bottom here, which looks very much like the Ogden hyperelastic model with some little bit modifications to it. And if you don't remember, Professor Ogden was a student of Professor Hill back in the day. So things are kind of interesting here, how they are mixed together. And I think that's probably why the different finite element programs have slightly different names on this type of model. The key feature of the Hyperfoam model, which is what I would call it here though, is that it can allow you to have a constant Poisson's ratio in your simulations. And that's really the main beauty of this type of approach. So in Abaqus, the Hyperfoam model has the equation shown in the bottom here. And this is exactly the same equation that's used by COMSOL multiphysics. And by having these power exponents written this way, you get this constant Poisson's ratio. So the Poisson's ratio is related to the beta parameter through these two equations here. And if you plot the predictions here, so this is stress strain predictions now. The blue line is mu equal to 1, alpha equal to 1. So that gives almost a straight line in stress strain space. If you make alpha to be positive, so this exponent on the principal stretches is positive and greater than 1, you get a curve that's concave upwards in tension, but flat in compression. So that gives you this asymmetry between tension and compression. But if you make alpha less than -1, you get the curve that is concave downwards in compression and flat in tension. So you can tailor the response in that way by picking these. But remember, in Abaqus, mu should be positive, the mu value should be positive. Alpha can be either positive or negative depending on the type of foam you're interested in. So that's how that works. Also, you can have an arbitrary number of these terms, like in the Ogden hyperelastic model, if you want to have symmetry between tension and compression. If that is indeed how your foam behaves, you would like to have some terms with positive alpha and some with negative alpha, as we just talked about. In Ansys, this type of model is called the Ogden foam. And it has the equation written at the bottom, which is very similar to the Abaqus one. But there's one major difference, and that is that the denominator here is just called alpha I. And if you go to the Abaqus page, I jump back, it's alpha to the square. So Abaqus puts a square on this. In Ansys, there is no square. So that has some consequences, because if you make alpha positive, it gives the same thing in tension. Like for Abaqus, you alpha larger than 1, you get the concave upward response. But if alpha is negative, then you should have typically mu to be -2. So you pick a negative modulus here together with the negative alpha gives you this response in compression, which is what you typically would like to see. So that's how Ansys does this, but otherwise it's very similar to the Abaqus representation. In LS-DYNA called this the Hill Foam. So kind of interesting, right? The equation is very similar to the Ansys equation. They have slightly different names of the parameters. They call them C and B and N. They use the lowercase n in the equation for the strain energy, but then they call it capital N when they specify this. So it's a little confusion there, perhaps. But otherwise, there is no square on the B parameter here. That means if B is negative, you probably want to have C to be -2 in order to get the concave increasing stiffness in compression, like you can see here.